All right, so last week we reviewed all the stuff that we can read, calculate, infer, interpret from a position versus time graph. Today we're going to go over the same stuff, but to do with the velocity time graph. So, what can I read directly off a velocity time graph? Velocity and time, yeah, that's what's on there. So I can look at a velocity time graph and know what the velocity of the object is at any point in time covered by the graph. Okay? From a velocity versus time graph, I can also infer or interpret the type of motion the object is undergoing. Okay? If it's traveling at a constant velocity, or if it's accelerating, or if it's accelerating in a non-uniform way. Okay? Those kinds of things from the shape of the graph. And then I can also calculate acceleration, displacement, and average velocity, okay, from that graph. So there's lots of stuff I can do with a velocity time graph. All right, so looking at these two graphs here, okay, the one on the left is a position time graph. That's what we looked at last week. What is that graph showing? Yes, but what type of motion? You're absolutely right, it is showing position and time. What type of motion is it showing? Velocity. Right, something traveling at a constant velocity in a forward direction. Okay? Could I calculate that velocity? Yeah, I could, right? I can go in and use my formulas, right, and say, okay, velocity is total displacement divided by total time. That would be my final position, 1,400 meters, minus my initial position, 100 meters, okay, and divide that by the time, 5. So 1,300 over 5 should be 260, I think, meters per second. Okay, positive. Right, is that okay? That's what we learned how to do last week. What is the graph on the right showing? Keeping in mind the one on the right is a velocity time graph. The same thing. In fact, not just the same kind of motion, the exact same thing. These two graphs are of the same object. Okay? This one is showing an object traveling at a constant velocity of positive 260 meters per second. So is this one. Okay? I mean, our velocity line goes right here, right? It's at just above 250, about 260, and it does it for 5 seconds. It's exactly the same object, just from a different point of view. Okay, this is looking at what is the velocity doing. Well, the velocity isn't changing. All right, now here's what happens. On an exam, I put a multiple choice question on that has that graph on the right. And I say, what kind of motion is this velocity versus time graph showing? A, object not moving. B, object moving backwards at a constant velocity. C, object moving forwards at a constant velocity. C, object accelerating. Obviously, B is the correct answer, but what do a lot of people pick? Object not moving. Okay? We always interpret a flat line to mean nothing's happening, which isn't true. A flat line means nothing's changing. It doesn't mean nothing's happening. There's something always happening on a graph. Time is going by. Okay? Even if the line is flat, time is still going by, so something is happening. Okay? Even something sitting still is something happening, it's just not changing. Okay? So we want to kind of get that idea of a flat line means nothing's going on out of our heads. Okay? It does mean that nothing is changing instead. Okay, on this position versus time graph, the object's traveling at a constant velocity, which means it's not accelerating. Would you agree? Okay, what would acceleration on that graph look like? Okay, Kelsey just went like this. Okay, would be a curve, right? An upward. If it was positively accelerating, it would be an upward curve like this. What would that look like on that graph? Spencer just went like this. You mean a diagonal line? Exactly. Okay, on this velocity versus time graph, okay, this would mean the object is accelerating. Because we would have a change in velocity happening over the course of time. Right. Now, in Science 10, you learned about acceleration, and they taught you that this is how you calculate acceleration. Final velocity minus initial velocity divided by time, or delta V over delta T. Does that look a lot like the formula I used right here? It's similar, right? At least in form. Obviously the stuff that's in it is different, but the pattern is the same. What did we say the slope of this line represents on this graph? Velocity, or speed, yeah. Okay, so what do you suppose the slope of this line represents? It represents the acceleration. Think about what you learned the definition of acceleration was in Science 10. Okay? The definition of acceleration is any change in velocity over time. That's why the formula is Vf minus Vi over t. It's the change in velocity over time. Everybody okay with that idea? Okay. Now, if I have the slope formula set up, is that the same formula? Okay. This would be my final velocity. This would be my initial velocity, and this would be x, right? So this would be b, this would be y, okay? This would be x. Okay? That's where that formula comes from. It's the slope of a line on a velocity versus time graph. Okay? Now again, that's not something I want you to memorize. Okay? It's something you can always figure out. Okay? It's very easy to figure out what the slope of a line on a graph represents. Okay? It always represents the change in whatever's on the y-axis divided by the change on whatever's on the x-axis. For us, the x-axis is almost always time. All right, back to this graph here. If I wanted to calculate the total displacement on this graph, how would I do it? Or did I already have it up there, kind of? Already have it up there, right? If I want to find the total displacement of an object from a position time graph, I go final position minus initial position. Okay? How would I find displacement on this graph? I can't use that formula, obviously, if the positions aren't on that graph. Is there a way for me to do it? Do I have a formula that tells me how to calculate displacement if I know something's traveling at a constant velocity and I know how long it does that for? Which formula is it? Yeah, this one. If I manipulate that for d, it's velocity times time. Can I read velocity and time off of this graph? Then I can use this graph to get displacement, even though position's not on. Okay. Now, here's the trick you probably memorized in Science 10. It's the area under the line. Does that sound familiar to anybody? Okay. So you probably got taught, even by me, that if you calculate the area under the line on a velocity versus time graph, that would calculate the displacement. And it's true. Because if I take this graph and make a rectangle out of it, okay, what's on the base? Time. What's the height in? Velocity. Base times height. Right? So it's the area underneath the line. Right? Average velocity times time. Now, what if the graph looks like that instead? Can I still do average velocity times time? Right, divided by 2. Okay? If I take the change in velocity and divide it by 2, which would be the height divided by 2, Okay? That'll tell me the average velocity. I increased my velocity uniformly from 100 to 500, okay, over the course of 5 seconds. Okay? That means my average velocity is halfway in between the starting point and the ending point. So if I take the height and divide it by 2, that's my average velocity. Okay? Calculating the area of a triangle is base times height over 2. So if I've got this triangle here and I calculate the area of that triangle, really what I'm doing is taking the height over 2 and knowing that that equals the average velocity, and then I'm multiplying it by time. So I'm not doing anything we haven't done before. I'm just using the fact that I can get the information from that formula from the graph, and then I'm just plugging it in. Okay? And in the end, that's your biggest tool for any graph. Okay? Remember that one of the key points for this lesson was understand that the formulas on your formula sheet are derived from graphs. Okay? So that means if I've got a formula on my formula sheet, there's probably a way for me to get the data that's in it from a graph containing that data, and then I can just plug it in. Right? That's what we want to be able to do. Okay? That's the skill we want to develop. Rather than memorize, we want to go, okay, this graph is showing me velocity and time. Do I have any formulas that will calculate what the question asks for using what I can get out of this graph? Oh, I do. Okay, I'm going to plug it in. Okay. All right. Is that ringing a bell from last year? Okay, that velocity time graph there. Okay. Okay, so this is a velocity versus time graph of a person running a race. Okay, what are they doing in the first 5 seconds? They're accelerating. Is it uniform or not uniform? Like, is their acceleration constant for the entire? It's not, right? At the beginning here, it's a little bit curved. Okay, and that's okay. If you get a curve on a velocity versus time graph, it still means an acceleration is going on. It's just not uniform. Okay, if I dropped something, I would get a perfectly diagonal graph because it would accelerate at 9.81 meters per second squared all the way to the ground. All right, but in a situation like a race, when you first come out of the starting blocks, your strides aren't all the same length. Okay, maybe you're slipping or stumbling a little bit, so your acceleration's not perfectly uniform. Okay? Once you get upright and you're now running properly, your acceleration becomes pretty uniform until what? Can you accelerate all the way to the finish line in a 100-meter race? No. You're going to hit your what? Yeah, you're going to hit your limit. You're going to hit your top speed. Okay? And then you just, doesn't matter how hard you try, you simply can't run any faster. Okay? All the forces working against you are balanced with the force working for you. Okay? So you got wind resistance, you got friction on the ground, all that kind of stuff, and it all just balances out. You simply cannot make your body go any faster than that. Okay? Even though you're pushing just as hard as you were before. So that would be this part of the graph. Okay? Runners running at a constant speed, their top speed, which is not very fast. 8 meters per second is not very fast for someone to run. Okay? And then, what happens here? They probably got to the finish line. What do you typically do when you get to the finish line? Stop. Yeah. Does that person stop? Does their velocity reach 0? They stop. Okay? So that's what a graph of a runner, okay, running a race would look like. A slow runner. Right? Just so you know, because like Usain Bolt, his top speed is like 17 meters per second. Okay? It's ridiculous. But when you're 6'7" and when you're running at top speed, you're covering like half of this room in one stride. Okay, you can really, make some good time. Okay, when you're doing that. Okay, now, does everybody's graph end up with a similar shape, no matter how fast or slow you are? Typically, yes. Okay, you're all going to have an acceleration phase, a top speed phase, and then your stopping phase. Okay, but where that graph sits, okay, is an analytical tool that, let's say, coaches or trainers might use to help improve their athletes' performance. Okay, for a guy like Usain Bolt, his graph certainly has a shape generally like that, but he's actually a terrible accelerator. Okay, if you've ever watched one of his races, he's like the last guy out of the blocks, and he's always at the back of the pack at the beginning of the race, like for the first 30 meters or so, okay? Once he gets upright and gets to his top speed, however, everybody else in the race is doing this, because they can hear him coming. Okay? I mean, he just, once he reaches his top speed is so incredible, okay, that he just runs everybody down. Okay? I have never watched the race, I've watched a lot of his races, where he ever led from start to finish. Okay? That's just not the kind of runner he is. Right? His trainers and coaches have maximized his top speed. They knew that as a tall, lanky fellow, okay, he was never going to be very powerful. Okay? He was not going to have a strong first, let's say 50 meters of a race. But if he could have the best last 30 meters of the race, he could win. Okay? It's actually why he's a better 200-meter runner than a 100-meter runner. Okay? When he gets to top speed, he's in good enough shape that he can hold that 17 meters per second for 150 meters. Well, nobody is ever going to beat him, okay, if that's the case, because nobody else can run that fast. So the only hope other sprinters have of beating a guy like that is maximizing the first part, getting to their top speed more quickly. Okay? So being powerful. It's why you often see two body types in sprinters. Okay? You see the Usain Bolts and Donovan Baileys and Andre DeGrasse types, skinnier, but really, really fast top speeds. And then you see the gigantic, hulking bodybuilder type sprinters. Okay? Those guys are very powerful. Okay? They accelerate very quickly, but their graph looks different. So I'm basically telling you, there's like practical applications for this stuff. For football players, this is your 40. Okay? That's the science of using the 40-yard. Okay, to kind of build your power and maximize your power, and what kind of exercises you should be doing to increase your power. Okay, is looking at those numbers. Bobsledders, same thing. Okay, you never see a bobsledder built like Usain Bolt. Okay, you never be able to fold them into a bobsled, for one. Okay, and secondly, top speed makes no difference at all. It's all about power and pushing the sled. Okay, so there's a lot of athletic training science that is tied into graphs. Okay, position time graphs, velocity time graphs, things like that. Okay, analyzing where someone has their strengths or not. Okay, questions on that one? Okay. All right, so on a velocity versus time graph, what can we read? Well, we can read the instantaneous velocity at any point in time, because we can read that directly off the graph. Okay, and we can calculate the displacement by finding the area under the line, or using average velocity times time to get the displacement. Okay? And the other thing we just talked about that we can calculate is acceleration. Okay? Vf minus Vi over t, okay, is also equal to the slope of a single linear function on that graph. So when we do our acceleration lab next week, okay, we'll be using velocity versus time graphs and doing this kind of stuff. Okay. Okay. Is that sounding familiar from Science 10 at all? I haven't taught you anything new. That's all stuff I would have taught you in Science 10 if you hadn't. Okay. On this graph, which data set shows the greatest acceleration? Which run has the greatest acceleration?
Run 5.
Right, run 5, okay? The orange set of dots here. Okay, how do we know that? It has the steepest slope. Okay, on this graph, whichever one changes its velocity the fastest, okay, and that's how steep the line is the fastest accelerator. Right, so run 5 would have the greatest rate of acceleration. What would that rate of acceleration be? What part of the graph did we say represented acceleration here? slope of the line represents acceleration on this graph, yes? Okay. So that means then that the rate of acceleration for run 5 is 7.61 meters per second squared, or meters per second per second. Okay, I would like for you to calculate for me I'm just going to put a couple of questions on here, guys. I want you to see if you can calculate these values for me, okay? Possibly using these equations here. Okay, give those ones a try. I'll give you a little bit of time to get ahead of me. Number 3 we'll probably have to work through together because I haven't really covered how to do that from this kind of graph. All right, so for number 1, it wants the velocity after 6 seconds for run 1. Okay, since this is a velocity versus time graph, can I use y equals mx plus b to get that number? Absolutely. Okay, y is the velocity, x is the time, and m is the acceleration. Okay, b represents my initial velocity on this graph. Right, so all I have to do is solve for y, since that's what's on the y-axis. Okay, so if I want to solve for the velocity after 6 seconds, I'm going to put in the slope for run 1, 1.28, multiply it by 6 seconds, that's the time, that's x, okay, plus my initial velocity of negative 0.0885. Okay, if I do that, that'll give me the velocity of the object after 6 seconds. Okay, so 1.28 times 6 plus negative 0.0885. All right, so we'd be looking at it moving at a velocity of 7.6 meters per second. Right? And actually that should be positive since velocity is a vector quantity. All right, everybody follow what I did there? Okay. Did that involve me having to memorize anything, or did I just have to look at the graph and go, here's what everything represents? Okay. I mean, in the end, I've been doing this a long time. I do have that memorized, but okay, I would also want to be able to look at any graph and analyze it and say, okay, what's on the y-axis? Velocity. What's on the x-axis? Time. Okay, what does everything represent, and calculate from there. How many people have done number 2? Okay, is it similar, but we're solving for something different? What are we solving for instead? X, yeah, we're solving for time. How long does something take? Time is on the x-axis. So So for question number 2, we're going to go x equals y minus b over m. Okay, so that'll be 10 meters per second, and it was for run 2, so minus 0.0333. Okay, and divide that by the slope, 2.4, okay, and we'll have the amount of time it takes. Okay, so the 2.4. All right, so it's going to take about 4.2 seconds, okay, for us to do that. Okay, is that basically like what we learned how to do on the position time graphs? Yeah, just we're calculating different things because it's a different graph. Okay, same math, it's still manipulating y equals mx plus b. We just have to remember that those things, y and m and b, represent different things on this graph than they did on the other one. All right, the last thing here is we got to calculate the total displacement to 0.3 seconds. All right, now we just said that total displacement means calculating average velocity multiplied by time. In other words, the area under the line. But here's what I have to remember about this object. Did it start from rest? Did run 5 start from rest? Did any of the runs start from rest? Okay. According to these, they all had some initial velocity, even if it was negative or very, very small. Okay. None of them actually started from rest. Okay. They all had some initial velocity. Okay. Run 5, however, has got the biggest initial velocity. So what that means is there are 2 shapes under that line. Okay? If I just calculate the area of the triangle, all I'm calculating is how far it went during the acceleration. I'm not taking into account that it didn't start from rest. I also have to add on to that how far it would have gone in that time had it traveled at its initial velocity. Okay? So I've got the rectangle and the triangle that I have to account for here. Okay? So there's basically 2 areas that have to be calculated. So that's going to mean doing this. Okay? Calculate the rectangle and calculate the triangle. So for the rectangle, okay, the base is going to be 0.3 seconds, and the height is going to be 0.285, my initial velocity. Okay, for the triangle's base is also 0.3, right? But the height of that triangle goes from 0.285 to, well, we don't know. Okay, at 0.3 seconds, that line's actually off the graph slightly. What do I do now? Can I calculate what the y value of that line is at 0.3 seconds? I can. I just have to use y equals mx plus b. All right, so I'm going to plug that in and say, all right, y equals 7.61 times 0.3 seconds, okay, and then plus 0.285. Actually, if I wanted to really do this right, I wouldn't even add that on there, okay, because I'm just going to subtract that in a minute, but we'll do the whole thing anyway. Okay, all right, so 7.61 times 0.3 plus 0.285. All right, so there's the value of y at 0.3 seconds. Is that the height of the triangle? The triangle starts here, not at 0. That value we just calculated is here. That's not the height of the triangle because the triangle only goes from 0.285 to that value we just calculated. So if I take off that 0.285, okay, there's the height of my triangle. So really what I'm doing is this. I'm saying the triangle is going to be 2.568? Yeah. And then down here, 0.285. So the height of my triangle is the difference between those two numbers. Okay. Everybody all right with that? A little bit of geometry in here. Okay. Not too bad though. Okay, so if I take that number there, okay, the 2.283, right, and divide it by 2, so height over 2, and then multiply by 0.3. Okay, so there's the area of the triangle, plus 0.285 times 0.3, the area of the rectangle. All right. There's the total displacement of that object, okay, to 0.3 seconds. Okay. How far it would have traveled if it didn't accelerate, plus how far it traveled while accelerating, and it gives us its total displacement. Okay. So what did I do here? Okay. Well, for this part, I took the initial velocity and I multiplied it by time. And for this part here, okay, I essentially did this. Essentially. Okay. Pick out your formula sheet. See if you have a formula that has those two things in it. Yeah, right? Right. This formula here is on your formula sheet. Displacement equals initial velocity times time plus 1/2 AT squared. Did I just do exactly the same thing using my graph? I did. I calculated displacement using that same method, right? Just trying to illustrate all the stuff in the formula sheet is derived from graphs, or some way or shape or form comes from a graph. Okay? All right, don't panic if that's like feeling a little bit out there, okay? We're gonna spend some more time on that stuff, okay, as we go along. Okay, I want you guys to see if you can do question number 6 there, so don't worry about this one here for now. Okay, number 6 has to do with this velocity versus time graph, okay? So it wants to know the snowmobile's average velocity during each of the segments. What two things do you need? Or is maybe there an even easier way to calculate average velocity here? Okay, I'll give you a few minutes on that one. See if you can calculate the average velocity for each part. Okay, let's quickly look at these here. Part B is probably the easiest one. Why is part B the easiest one to calculate the average velocity for? What's it doing in part B? Yeah, it's traveling at a constant velocity in part B, right? The graph is flat. It's showing that its velocity isn't changing. So since for the entire section there, part B, it travels at 40 meters per second, what's its average velocity? 40 meters per second, okay? It traveled at a constant velocity, therefore that is its average velocity during that part, right? The other two are also fairly straightforward, okay? In part A, we start at 0 meters per second and we accelerate to 40 meters per second. Okay? We just said a minute ago that if we calculated the area underneath this line, okay, that would represent our displacement. But to do that, we had to go height over 2 to get our average velocity. So would my average velocity just be the height of this triangle divided by 2? Should be. Half the time, would I be going faster than 20 and half the time slower than 20? Okay, that means my average velocity is halfway in between 0 and 40, 20 meters per second. And the same is true for the last part. Okay, that last part starts at 40 meters per second and goes to 80 meters per second. Okay, well, then my average velocity is halfway in between those, 60 meters per second during that part of the graph. Okay, so there's not really any calculating to do there. It's more being able to recognize what type of motion is going on, okay, and then go from there. Okay. With that graph, I would like you guys to calculate for me the total displacement of the snowmobile. Okay, give you a minute on that one. Okay, so at the end of a school day, student A and student B say goodbye and they head in opposite directions, walking at constant rates. Student B heads west to the bus stop while student A walks east to her house. Okay? After 3 minutes, student A is 300 meters east and student B is 450 meters west. Okay? Graph the position of each student on one graph after 3 minutes. All right, so if I wanted to graph their position, I would have a graph that would have to look like this. Well, I would have to put 0 in the middle.
They're headed in 2 different directions, so one's gonna go past west.
Right, okay, they're heading in 2 different directions. And so one of them has to be negative and the other has to be positive. Generally, we make east positive. So student A walks east to her house and in 3 minutes goes 300 meters east. So, let's just say that there is 300 meters, okay, and that here at the very end is 180 seconds. Right, so that would be student A. Okay. Student B, though, goes 450, okay, which is further. So they're going to have a slightly steeper line, and it goes down to 450 meters, okay, west. Right, so they're going to have a steeper line. Everybody okay with that? Okay. How come the other one didn't go like this? Right, they're not just going west, they're also going back in time. Okay, because I started my time axis at 0. If they go that way, they're gonna end up there negative 180 seconds earlier. No, that would still be later because the negative times. Okay. It'd be 180 seconds earlier, okay, if they went that way, which somehow means they ended up at home before school ended, which we know is impossible. Okay, everybody all right with that? So just make sure you're always kind of being careful of the wording. Now, would it be pretty easy for me to determine the velocity here? Okay, do I have their displacement? Do I have their time? I can just do V equals D over T, right? Okay, so it's a pretty straightforward or standard graphing question. All right, if I'm looking at this position versus time, or sorry, this question here, okay, with the different animals and how fast they run, okay? If I'm looking at this graph down below, which one of these lines, okay, is the moose? I'll label them here. So let's say A, B, C, and D. Which one of those lines is the moose? Somebody whispered it. C, yeah, okay. The moose took 12.9 seconds to run 200 meters. Okay, so if I'm looking at that, that means, sorry, I didn't have that scroll down very far, but he would be the second slowest slope, right? So that would be C. Whereas the elk only took 10 seconds to go 200 meters, right? So that would be the first one. He would have the steepest line, right? The coyote is pretty quick, okay, 10.4, he'd be B, and the grizzly bear would be 18 seconds. Now, to give you an idea here, okay, the world record for human beings for the 200 meter is more than 18 seconds. So you're not going to outrun a grizzly bear. Okay? Now, and that world record, remember, is under ideal conditions on a flat rubberized track where something is not chasing you down that wants to kill you. Okay? Grizzly bear will always have the advantage in nature because they can run that fast through the forest. You ever seen a grizzly bear on film running through the forest? They don't dodge trees. Well, at least the small ones. They just break them off. Okay? They just run right through them. Okay? So if you're ever going hiking, don't hike alone, or hike with someone slower than you. Okay? I always used to hike with a buddy of mine who was a physics teacher and a wrestling coach, and he was built like a square. He was about 5'4", okay, but about like 200 pounds, and just like a square. Okay, and I said, "You're a great hiking partner because I know I won't get eaten by the bear." And he said, "Do you realize how close to your knees I am?" I'm like, ooh, hadn't thought of that. So yeah, all right. So grizzly bears pretty fast. Okay, and that's a big, huge animal. Okay, we don't give them credit for how quickly they can cover ground. So you are definitely not going to outrun one in the wild. All right. So with this graph here, what is the shape of that position time graph? Yes. What does the shape of that position time graph tell us is happening? There is an acceleration. Is it speeding up or slowing down? It's slowing down. Okay, we have a curve, so we know it's accelerating. We know its velocity is changing. But because that curve is getting flatter, that means it's covering less distance every time interval, right? In the first second, it went that far. In the second second, it only went this far. In the third second, it only went that far. Fourth second, only that far. Okay? Fifth second, hardly anywhere at all. Okay? Getting slower and slower and slower. Okay? That's a pretty common multiple choice unit exam kind of question. Okay? Here's a position time graph. What kind of motion is it showing? Stopped, constant velocity forwards, accelerating, slowing down. Okay? Now, if I had accelerating and slowing down, which one's the best answer?
Accelerating would be in the negative direction.
Okay, if it said that, yeah, but if I just had accelerating and then for like C, and then I had slowing down for D, which one's the best answer? Slowing down. Yeah, it's more specific. Accelerating could mean speeding up or slowing down. Because D is specifically saying slowing down, that's the best answer because it's most accurate or most descriptive of that. Okay? I only say that because it comes up sometimes. People are like, well, that answer's also right. Yes, but the instructions on a multiple choice exam never say pick the right answer. They always say pick the best. It's very common, okay, for them to have two answers that are technically right. Well, one's always better than the other. Okay? I know that seems brutally unfair. Wait till you do a multiple choice exam. Yeah, so there's A, B, C, and D, and then there's 1, 2, 3, 4, 5. Okay, so 1, 2, 3, 4, 5 are options, and then A through D are options 1 and 2, 2 only, 3 and 5. So it's multiple choice. That is proof. Okay, yes. It's usually psychology when I do those. Okay. I want you guys to try those two. So they're both velocity versus time graphs. Okay, you don't have to draw the graph to scale. Okay, for number one, just kind of give me a rough drawing of what it would look like. All right, so 1 and 2 here, guys. I'll give you a few minutes on those, and then we'll walk through them. Okay, so for number 1, what is that object doing? It's accelerating in a positive direction. It's increasing its velocity. What does a position time graph of that look like? Right, upward curve. Done. Okay. All that question asks you to do is be able to analyze or interpret that graph. Okay. All right. Calculate the acceleration using the graph below. Okay. I got two options on that. I could do this, m times x plus b, right? My b would be 10, right? So I would just calculate the slope then, y minus b over x, okay? Because what I'm really doing when I do that is this. Which is the other way you could do it. Well, kind of the other way, it's sort of the same way, okay? So I would just put in my numbers here. Y would be 0, or VF would be 0, minus my initial velocity, which is my y-intercept, which on this graph is 10. Okay, and then I divide that by the time, 10 seconds. All right, so 0 minus 10 is negative 10, divided by 10 is negative 1. Okay, but do I want to write negative for my answer? What's my vector? This is in meters per second north. If I got negative, south. Okay, how many people missed the north? Yeah, okay, and that's easy. That's why we do that one as an example. You always need to look on your y-axis to see if they actually label the directions anything other than positive and negative. Okay, because sometimes they don't put positives on there, but they put in the label the direction. Okay, so I know that positive is north, that makes negative south. Okay, that's another one that I could put on a test and have, like, 1 meter per second squared, positive 1 meter per second squared, negative 1 meter per second squared, or 1 meter per second squared south. Okay, and I'd get a pretty big distribution of answers on that. Okay, questions on those two? All right, I would like you guys to try this one, keeping these formulas in mind, or this formula in mind. Okay, that one can help you with the acceleration because obviously it's not a single linear function, but you can still use that formula because you can read the final, initial, and time. Okay, and I think you guys can calculate the displacement as well from that one. It's very similar to the snowmobile question. We just kind of flipped the line. So. Okay, let's do part B first. It's just quicker. Okay, if I want to calculate acceleration and I have a velocity versus time graph, I can just use this formula here. I just have to plug in the values as I read them off the graph. All right, the final velocity of this object is 1 meter per second east. Okay, and the initial velocity is 3 meters per second east. Okay, and the total time for that is 10 seconds. Okay, so if I do that, okay, 1 minus 3, I should get negative 2 over 10, which should give me 0.2 meters per second squared west. Okay, this thing is moving east, but it's slowing down. In order to slow down, you have to accelerate in the other direction, okay, which is what this object is generally doing over the whole trip. Okay, I mean, in reality, the first part of the trip, it's traveling at a constant velocity. This is really the only part where its velocity changes, and then there's a constant velocity again after that. But over the whole trip, on average, okay, the acceleration is 0.2 meters per second squared west. Okay, again, got to watch out for them giving us the vector on the label. Okay. All right, I want to calculate the total displacement. What should I start drawing on here? Yeah, you gotta start drawing some shapes. Okay, so I'd have this big rectangle, that little triangle, and that rectangle. That would be my least number of shapes to calculate. Okay, that would give me the area under the line, which would be 3 different average velocity times time calculations. Okay, so for this rectangle here, I've got a height of 3 and a base of 4, so that's going to be 12 meters. For this triangle here, I have a base of 1 second and a height of 2. Okay, so 2 times 1 is 2, divided by 2 is 1 meter. And then I've got this rectangle here that has a base of 6 and a height of 1, so it's 6 meters. All right, so we should be looking at 19 meters. Okay, and that would be east for our total displacement tank. Okay. That stuff ringing a bell from Science 10? Okay. This is like my favorite question. in terms of velocity versus time graphs, because it's an interpretation question. Doesn't involve really having to do much calculating of any kind, okay? So for part A, they're asking whether the acceleration is positive, negative, or 0 for each section. So in section A, right here, is the acceleration positive or negative? Negative, right? It's getting its velocity to be greater in a negative direction. Okay? It's speeding up backwards, basically. What's the acceleration here? Zero. Okay? It's traveling at a constant velocity there, right? Acceleration is only occurring if the velocity is changing, and in part B, it's not changing. Right? In part C, positive or negative? Negative. It's going faster in a backwards direction or negative direction. D, 0. E, the positive acceleration. Okay? And then in the last part, F, 0. It's not accelerating in F because the line is flat. Okay. So this is supposedly a graph of a bird. Okay? Part C wants to know, when does the bird change direction? So at what time on the x-axis does the bird change direction?
Is it at 0? Like goes, it's the graph.
At 0, like 0 on the y-axis or 0 on the x-axis?
0 on the y-axis.
0, yeah, okay, so when it gets to 0, yes, it would be changing direction. So what time does that happen at?
Oh, 8 minutes.
Right here at, yeah, 8.5 seconds. You know what the most popular answer is if I ask that on a test? 7. Okay, why is 7 the most popular answer? Because the line changes direction there. Okay, but this is how that question tells the difference between someone who sort of understands graphs and someone who really understands graphs. Okay, so on this graph here, during this section of the graph, is the velocity of the bird still negative? Okay, on this section of the graph, the velocity of the bird is positive. So it is at that point right there where the bird changes direction. It starts to accelerate in the other direction at time 7. Okay? That's where the acceleration becomes positive. But the bird's not going forwards yet. Okay? So essentially, this section of the graph would be like if somebody strung a bungee cord across the front of the classroom. Okay? I come running at that bungee cord. Okay? I hit the bungee cord. I'm still going this way. But I'm accelerating that way. Okay? So my graph would look just like that one. I'm still going forwards, okay? But I'm accelerating backwards until I stretch the rubber band far enough that now I can't go anymore, and the rubber band starts to shoot me backwards, okay? That's where at that point, my velocity would start to be backwards. But the whole time, my acceleration would be the same value, okay? Everyone okay with that? The same is true if you throw something up in the air, okay? The graph of throwing something up in the air looks like this. Okay, this is meters per second. If I throw something up in the air, it goes up and then comes back down. Last time I checked. Okay, pretty sure that's still true, right? But that's what the graph looks like. That graph shows something constantly accelerating in a negative direction. What's the slope of that line if it's something thrown in the air? Negative 9.81 meters per second squared. Okay? But at this point right here is where that object is at its highest point, where it stops for an instant. Its velocity is 0 meters per second. Okay? And then it starts to fall back down. Okay? After that point, its velocity is negative. Okay? And its acceleration is negative. The whole time, its acceleration is negative. But here, that's where you threw it. Okay? That's where it was moving the fastest. It just left your hand. Okay, has its highest velocity, slows down, slows down, slows down, gets to 0, starts to fall back down. It's weird that we would look at that and see it do something that changes and see a line like this that says the acceleration is constant. Well, it is constant. Okay? So that's that whole wacky world of interpreting graphs. Okay? Now, spoiler alert, I always put a question like this on the unit exam. To be ready for that one. Okay? All right, I think, guys, we will call it there for today. You may. So tomorrow is Tuesday. What do you have on Tuesday? This one is going to have graphs on it. Probably one of each. I will post a practice quiz today between 3:20 and 3:30 with a solutions video. Take the time to do it and watch the video.